Welcome to Mathlink Academy, where we connect the dots. I am Mr. C, and in this unit, we're going to look at using the substitution rule in integration. So we're going to use integration by substitution. So let's get started. Basically, we understand the basic integration rules. For example, and I've seen like this computer wants to do it too. Our different integration rules. By now. So our basic integration rules will be this.
I'm not sure I understand.
Well, you're going to understand at the end of this. So we have this, guys. F of x is equal to, let's say, 3. Or we just integrate 3 dx. Basic rule will be 3x plus c. This is indefinite integral. Now, as we get to more complex fractions or functions, we have 3x dx or e to the x dx. That's the same thing as e to the x plus c. Or even having the sine of x dx. In this case, don't forget this will equal to the negative cosine of x plus c. Now, these are basic ones we know. If we know the basic ones, then we can have some more complex ones. And then at times we can use the U-Substitution. That's what we call it, the U-Substitution, integration by substitution. So if we get a little bit more complex, and we're going to use something like, some people call it like a reverse chain rule. And I'm going to show you how to use that particular one using some examples. So again, we want to look at some outside functions and some inside functions. For example, you'll be able to, at the end, be able to integrate something like the cosine, let's say the cosine, and in parentheses, not just x, but let's say it's 3x plus 1 dx. You say, wow, Mr. C, that is just not the cosine of x. I can't do that. But if it was the cosine of x, I can do it. But since it's 3x plus 1, then we use something with U-Substitution. Or you may be able to integrate functions like this. Let's say you have x cubed plus 1, and then times, let's look at this. Sometimes you may have something like this. 3x squared dx, and then let's raise this to the 5th power. I'm making it a little bit complex. In this case, we can use that U-Substitution. I'll show you that later. It's a little complex. Now, if I didn't have that to the 5th power, let's say I didn't have that 5th power. I want to get rid of that. I could just distribute this and use just our power rule for integration. But since I do have this to the 5th power, it makes it a little bit difficult. You can actually multiply x cubed plus 1 5 times. That's going to take a minute. And then do those individuals when you multiply 3x squared to it to figure out what it is by power rules. But by the time you figure out the answer, I'm already in bed taking it easy, and it's the next morning. So these are ways we look at more complex type of problems. Now, looking at this one right here, the last one I just wrote, basically what you're doing is you're trying to find an inside and outside function and a derivative at the same time. So we know that this is a function inside x to the 5th. And basically what you're going to try to do is find a derivative in the original piece and then substitute. That's what we call it U-Substitution. Okay, taking the derivative of this here, of that function, if this is f, taking the derivative of it to give us, see a form of f prime in the original function. And same thing with this one right here. This is an inside function, and an outside function is the cosine of, in the parentheses, that's an outside function. And then you got to take some derivative. So let me show you on our slide what I mean by that. So here's our differentiation of a composition function or a composite function. So let G be a function whose range is in some interval of I. I'm going ahead of myself there. And let F be a function that is continuous in I. If G is differentiable on its domain, and f, capital F, remember capital F is the antiderivative of f on I, then we have this. We want to enlarge this so we can see it a little bit. And don't get so caught up in this particular rule or definition that we're looking at. I'm going to show you how we easily can do this. So we have this inside function. I want you to see this. G of x, and the outside function is f. That means if we have some form of the derivative of that g prime in the original, our final answer will look like this. All we do is have the capital F. That means we're taking the integral of that function f, make it capital F, and then just inside would be the original g of x. And then don't forget, since it's indefinite, it'd be plus c. Okay? Now, how we do that, we call it, we have U-substitution. And this is where we got to be intuitive of understanding what function we're going to call g. So you're going to have to decide what function you're going to call g of x, and then take that derivative and then substitute into the original function and take the function with respect to u, if that's the letter we're using, that's what we're going to use, and then refer everything back to x. I'll show you that in a second. So let's look at this, guys. So you say, well, I'm going to let u equal to this g of x. Then I'm going to take the derivative of g of x, and that would be replaced by my du, and I'll show you that in a second. So in this case, this function here is the same as this function, but all I did was I let u equal to g of x. You're going to have to find out what u is equal to when you look at these functions. So let me try to give you a bigger picture of what I'm saying here. So let's look at a bigger picture of this, and this would be right here. So our outside function is f. Our inside function is g. The derivative of the inside function is g prime of x, and this is all in the original problem here. This is what we're looking at. It's going to give me an answer of capital F with g of x plus c. Okay, and we have to look at some pattern recognition, and it's best to show some example of what we're talking about. So I'm going to start with some simpler example, and then hopefully you can see the pattern of how to use U-substitution to solve a little bit more complex of integration problems. So here's a problem right here. I want to integrate x squared plus 1 quantity square times 2x times dx. So in this case, I'm going to look at this. I'm going to say you have to decide. I'm going to look at that as my inside function, kind of like my g of x. It's going to equal to x squared plus 1. My outside function, write it in blue, is really x squared. That's the outside function, my composite function that gives me that function of x squared plus 1 quantity square. Now, let's go back to our g of x. What's the derivative of g of x? G of x is equal to the derivative of 2x. Now, in this case, how we can write it, we'll say is 2x, and I'll say for right now, dx. Technically, I'm a little off on that, but I'm just going to show you how we write it as that. If you notice that this piece is right here, okay? And then we also have our g, or f of x, or g of x, excuse me, being x squared plus 1, and we know the outside is there. So what I'm going to do, I'm going to clear this, and I'm going to show you how we call U-substitution. So let's just go strictly right into how to solve this. And this is just one way. I'll show you another way later, real quick. So what we do is you have to say, okay, can I brutally do this? And you can, but I'm not going to do that for right now. I'm just going to use U-substitution. That's what we call it, U-substitution. So you have to say, okay, what I'm going to let U equal to. Let's try it. You may have to do trial and error. It may not work the first time to what you let U equal to. So you say, I'm going to let U equal to x squared plus 1. Because what I see here, I'm going to let U prime is equal to 2x dx. In other words, I'm going to write this so we can see it like this. This is du with respect to dx. Du with respect to dx is equal to, taking the equation u with respect to x is equal to 2x. That implies, I'm going to put this here, that implies that du is equal to 2x dx. And that's correct. So now I'm going to put a check here, put a check here. This here is exactly this. So now we're going to rewrite the integrand with respect to u. What do you mean by that, Mr. C? I'm going to integrate. This is what u is, so it'll be u squared, and my 2x dx is going to equal to just du. All I did was substitute. Now that's easier to find with respect to u. We just use the power rule. This gives me u cubed over 3 plus c. What I did was I integrate now with respect to u. And now I substitute back in, since my original equation was in terms of x, I substitute back in what u was. In this case, u is x squared plus 1. So I say x squared plus 1 cubed divided by 3 plus c. And that would be my answer for this problem. Okay, and we'll go over a few problems to understand. The key is you have to let something equal to u, and you got to kind of see the derivative in the function or in the problem that you're doing, in the integral. So if you can see some relationship, that will help you out, okay? Now we're at our whiteboard, and let's do another problem. Let's integrate this. And you say, Mr. C, this is really long to integrate. I can't see how we get started. Well, we won't be able to do basic for right now integration, so we're going to use U-substitution. And there's other ways to do this, and there's other types of rules, but we're going to introduce just U-substitution. So for this one, let's say we let U equal what? What do you want U equal? Where do you see the derivative? Do you see a derivative somewhere here? So in this case, I'm going to let U equal to 3x squared plus 4. And the reason I'm letting that happen because I see du with respect to dx. If I take that equation u with respect to x, it's going to give me 6x. Okay. Notice I see a 6x up here in the original equation. So let me show you this, guys. This implies that du is equal to 6x dx. All I did was move the dx up here. So now this is exactly, we want to have it exactly the same. That's my du. Here's my u. And so let's integrate, rewrite this integration with respect to u, take the integration with respect to u, and then substitute x back into the final answer. What do you mean by that, Mr. C? We said the integral. And then we have u to the 5th. That's what we have on the top, u to the 5th times, this is exactly du. Now that's easier to integrate with respect to the variable u. just using that power rule. This would equal to u to the 6 over 6 plus c. And then our final answer, we got to substitute because our original problem was in terms of x. We got to substitute back in that u is 3x squared plus 4. So this would be 3x squared plus 4 to the 6th power divided by 6 plus c. And that'll be my final answer in terms of x. I don't want to keep it in u. Now I'm using the letter U because we call it U-substitution. You can use another letter, W or Z, but we usually use U for U-substitution. And that's my answer. Let's look at this particular problem. I want to find the integral of the square root of 2x plus 1. That's inside the square root, dx. A little different. You're like, Mr. C, how can I do this one? Since we cannot do it as a basic rule, we're going to convert it to U substitution, take the integral with respect to U, and then substitute the x back in, whatever we let U equal to. So in this case, let me show you. Let's look at this problem a little differently. This can be written as 2 to the x minus 1 to the 1/2 power dx. So all I did was rewrite the original equation. That helps me look at it a little differently because now I'm thinking about letting this 2x minus 1 being my u. I'm going to show you why. So we're going to say let u equal to 2x minus 1. Well, let's just let that happen. So what is du? Du with respect to dx is going to equal to just 2. Now that implies that du is equal to, I'm going to move this over here, it's going to equal to 2dx. Now, I don't have exactly 2dx in the problem, but I do have a dx. Okay. But one good thing about constants, you can force them into the problem as long as you balance it out. So watch this. Watch what I'm going to do here. So I'm going to rewrite this problem and watch what I'm going to do. I'm going to say the integral, using this one up here, of 2x minus 1 to the 1/2. I'm going to force a 2 be here. dx. You only do this with constants. But I just changed the problem because it didn't have a 2 there. Because I want to substitute this to be du. I want du here. Now, if I force a 2 inside, on the outside of the integral, I have to take the reciprocal to make sure the problem stays the same. So note, what is 1/2 times 2? It's equal to 1. So really, I didn't change the problem. And that's basically what we're going to do. Sometimes you got to put a constant in. Only do this with constants. You can't do this with variables, only constants like numbers 1, 1/2. You put that constant in. And then on the outside, you just take the reciprocal because when you multiply it all the way through, it's just only 1. You didn't change the problem. 1 times anything is itself. So in this case, this is going to equal to, I'm going to write this in blue in terms of u. My outside is 1/2. Now that 1/2 came because on the outside of the integral, because I want to balance out that 2 I put in there. This would be u to the 1/2. And this would be du because this is what du is equal to. Now we'll just use our basic power rule. We'll go back over here. So this gives me 1/2. This would be u to the what? We do 1/2 plus 1. This would be 3/2 divided by 3/2 plus c. Now you don't write that as a final answer. So let's do some, that's a complex fraction, u over 3/2, and then you get times another half. So another way of saying this is, and I'll write it over here, it's saying 1/2, that's the outside, times 2/3. You take the reciprocal, what's on the denominator, u to the 3/2 plus c. Multiply it out, we end up with 1/3. And then our final answer, I'm going to erase this. So our final answer, if we want to write it, we have to write it in terms of x. So let's erase some of this here and have a final answer. And that's why it's good to have a good whiteboard, just erase everything. So I'm going to erase everything that I have here, except the last thing I wrote to give you a final answer. So I'm going to underline what I have so far. And so the final answer, you write this. This is equal to 1/3. That's what this is. Our u, it was 2x minus 1 to the 3/2 plus c. And that'll be my final answer because I got to write in terms of x. Let's look at another problem. We have 3 times the quantity of 3x plus 7 to the 4th power dx. Wow, Mr. C, you're getting some problems here, and we want to integrate that. Now we're going to use U-substitution. You got to see what will you let u equal, and is there the derivative or something close to it, to the derivative that we can find in our original problem. So in this case, I'm going to let u, and I think you see it, is equal to 3x plus 7. That's the inside function. The outside is going to be that parenthesis to the 4th power. In that case, we have du, take the derivative of that function with respect to x, will be 3x. Oops, not 3x. It'll just be 3. There we go. And then don't forget, just to find du, we'll just move that dx on the other side. This implies that du is equal to 3 dx. Okay, so that's what we got to find in our original problem. Now notice this is a multiplication. This is 3 times that times this. These are all multiplied. That's where the red dots are at, right here. So in other words, we know multiplication is a commutative law. A times B is the same thing as B times A. You say, how does that work with us? Look here, guys. That's the same thing as 3 times dx. Even though the 3 is outside, it's all multiplying. We could rearrange this. So I could rearrange this. This is equal to the integral of 3x plus 7 to the 4th times 3 dx. And there's my du. So another way to rewrite this in terms of u, I'm going to do it in blue now. It'll be the integral, I'm just looking at this, the integral of u to the 4th times, this exactly is the same. I didn't have to force a constant in and put one on the outside because there's a 3, times du. There's my du. And in this case, this is equal to u to the 5th over 5, if we do in respect to u, plus c. And then we substitute in what is u. U again is 3x plus 7 to the 5th divided by 5 plus c. And then that will be our final answer. Again, it's plus c because it's an indefinite integral. Now let's do similar problem. Let's do a similar problem. Let's do it again. Let's say we had 3x plus 7 just to the fourth dx. Now, I am not going to multiply 3x to the 3x plus 7 4 times. That's going to take too long. So I'm going to use U-substitution. So let u, I'm going to put underneath there, let u equal to 3x plus 7. The inside function, again, we're looking at that inside function. And then du with respect to dx would be equal to 3. This implies that du is equal to 3 dx, just doing cross multiplication. Now we have our u, here's the u, here's our u piece here. And we're close with this. We have a dx, but we don't have a 3. So what I'm going to do, watch what Mr. C is going to do. I'm actually going to force a 3 in here. I'm going to put a 3 right here. Now what I did was I changed the problem by putting the 3 in there. And I call it the BAM method. BAM, I put a 3 in there. But now, to make sure I don't change the problem, I'm going to take the reciprocal of 3 on the outside, which is 1/3. I only can do this with constants. I put a constant in, bam, I force a constant there. But then on the outside, I give the reciprocal of it so I don't change the problem, because 1/3 times 3 is equal to 1. So I really haven't changed the problem. So there's my du. Here's my du. It's right there. So when I do this problem, I'm going to do it in blue. It's going to be 1/3. I'm going to put the, in terms of u to the 4th, and this is exactly du. You only can substitute du when you see it exactly there. Now in our case, we integrate with respect to u. So this is 1/3 u to the 5th over 5 plus c. Don't forget the plus c. And then we'll write this down as u to the 5th divided by 15 plus c, because we multiply that fraction, and then put our final answer back in terms of x. 3x plus 7 to the 5th power divided by 15 plus c. And that's our final answer. Let's look at another problem. Again, you may want to pause this and try this on your own and see if you can integrate this particular problem. So give yourself a minute to try this and pause it, and then we'll do it together as a group. Now for this problem, I will use U-substitution, and I have to see what I'm going to let u equal to. So again, you decide what u would be. For me, I'm thinking I see the derivative in this function if I let u equal something. I'm going to let u equal to x cubed plus 2, what's inside the radical. I'm going to rewrite this radical because I could write this as the integral of 3x squared times x cubed plus 2 to what power? To the 1/2. And a lot of times you want to rewrite it so you can see those powers. Okay. Now, in this particular problem, if I let u equal to x cubed plus 2, then du by itself will equal to 3x squared dx. So I'm already moved the x on the other dx on the other side. And I saw that derivative. I saw that if I let u equal to x cubed plus 2. Now look up at the original problem. We have that here. This is exactly du. I don't have to bam in a constant. It is exactly right there. So how do I rewrite this problem in terms of u? Look at this. So this would be the integral of u to the 1/2, because we remember u is x cubed plus 2 times just du. That's that green piece. This is the green piece. This is du. Now, what I'm going to do, I'm going to integrate u to the, this would be 3/2 divided by 3/2 plus c. When I continue with this problem, this will equal to u to the 3/2, and I'll take the reciprocal of this, or 2/3 plus c. That's how you get rid of that complex fraction of a fraction. Take the reciprocal. Now, my final answer, because I'm not done, because it's all in u's, but I have originally x, will be 2/3, you can write it like this, times my u is x cubed plus 2 to the 3/2 plus c. And that's my final answer because I'm putting it back in terms of the original variable, which was x. Let's look at some trig functions. Let's say integrate a trig function. So let's say we have the secant square of x times the tangent of x dx. I'm going to add a little caveat to this one. I'm going to put a 2 in front of here. So let's integrate that. You say, oh, Mr. C, you're using trig functions? No problem. You know your derivative of your trigs. So your question is, do you see a derivative of one of the other? And don't forget about that 2. I'm sure what I'm doing with that 2 out there. So in this case, I'm going to factor out a 2. Sometimes it's good to keep the 2 in. Sometimes you need to factor it out to make it a little more simple for you to see. So we have factor out the 2, because that's a rule we can use. So it'll be secant of x times the tangent of x dx. Now, what I think I know and you know is that the derivative of the tangent of x is secant square of x. And if that's the case, watch what I'm going to do. I'm going to let u equal to the tangent of x, and du will equal to the secant square of x dx. Again, that piece in green, the secant square of x dx, is right there. That's exactly du. And similarly, you can see the relation between sine and cosine. So you know the derivative and how that is, and you got to watch your negatives. So if I rewrite this, let's do blue. I'm going to say 2 on the outside, the integral of the tangent of, and I'm going to say the tangent is u, and this green piece that I circle is du. That is exactly du, the secant square x dx. Now to do the remaining part of this function, this would be u, or 2 times u square over 2 plus c. The 2's would cancel. I'm only going to end up with u squared plus c, and therefore my u would be tangent square of x plus c, and then I circle it like this. And that's my final answer. Again, looking at u being the tangent of x, and I see the derivative is going to be right here. That's my du. So all I'm left with is 2, and I factored on the outside. So that's why I have u, 2, u, and du times du. Again, these are just some basic U-substitution. There are more complex ones that I have on my Mathlink website. So make sure you look at the Mathlink website and look at some of the supplementary material that we have there, that you can look at other U-substitution. Again, look over the video, have more questions, and look at some of our material that we have on our Mathlink website. And again, let Mathlink bring it together.